Hello everyone. Today we'll start with the third part of the coordination compounds. In this video, we'll discuss valence bond theory. Before this, we have discussed the introduction and Werner's theory. So, valence bond theory for coordination compounds. Valence bond theory was developed by Linus Pauling. The main assumption made by him was that the metal and ligand bonds are formed by the donation of one electron pair by the ligand, donating of one electron pair by the ligand to metal, and thus form a coordinate bond between the metal and the ligand. So basically, he said that ligand has a electron orbital containing electron, and the metal has an orbital vacant filled, and both the electrons are transferred from this filled orbital to the vacant orbital of metal, and a coordinate bond is formed between ligand and metal. So uh, this uh, this is the figure for that vacant metal hybrid orbital. When ligand orbital containing a pair of electrons, they join and the electron donation occurs and a coordinate covalent bond is formed between the metal and ligand. Features of valence bond theory. The central metal cation uh, or atom makes available a number of vacant sp or d orbitals equal to its coordination number to form coordinate covalent bonds with the ligand. So basically, these coordinate compounds are generally formed by the coordinate compounds are generally formed. Coordination compounds are formed by the d block elements. So d block elements, in the first row we have scandium. Let me just write first. Okay. We have scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper, zinc. So the outer electronic configuration for scandium is 3d1 4s2. For titanium it is 3d2 4s2. For vanadium is 3d3 4s3. Similarly for chromium 3d5 4s1. Manganese it is 3d5 4s2. Iron it is 3d6 4s2. Cobalt it is 3d7 4s2. Similarly, it has nickel has d8 3d8 4s2. Copper has 3d10 4s1, and zinc has 3d10 4s2. So just remember this thing. So what happens when a metal has, let's suppose I am taking manganese. Okay, manganese outer configuration is 3d5 4s2. So what happens? The d electron 4p is 0. So to make a bond, we first draw the outer electronic configuration for this. This is the outer electronic configuration for manganese. So for 5 electrons are filled over here, 1, 2, 3, 4, 5. S has 2 electrons and P has nothing. So 3d5 4s2. This is how we will be filling electronic configuration for metals. Okay. So if a ligand, let's suppose ligand like H2O is binding, manganese hexa aqua, let's suppose if we are trying to form a manganese hexa aqua, this perchlorate coordination compound. So for this, how will you write the electronic configuration? To write the electronic configuration for this is for manganese. So for manganese plus 2, the electronic configuration will be 2 electrons from the s orbital will be removed. That means the s will be like this. The electronic configuration will be like 3d5 4s 4p. It is a little bit confusing. Let me just erase the things. Okay, coming back to the example that I'm showing you. As per the central metal cation, first it makes available the number of vacant orbitals. So, in order to generate manganese hexaquasec perchlorate, what has to be done? Manganese has to provide space for the aqua ligand to donate its electron. In this metal complex, manganese has an oxidation state of +2. How do I calculate that? Uh, you have seen in previous video that manganese hexa aqua 6, the two over here goes up here. So it is like this. So the electronic configuration of the oxidation state of manganese X plus 6 H2O is a neutral molecule. So charge is 0 is equal to +2. That means X is equal to +2. So manganese is in +2 oxidation. Manganese has a +2 oxidation state. Okay. And now we understood that manganese has an electronic configuration of 3d5 4s2. So for manganese plus 2, what will be the electronic configuration? Electronic configuration would be 3d5 4p0 over here. 3d5, 2 electrons from s will be removed. So I will draw the orbitals, that is 3d5, 4s is this, and 4p is also vacant. 4p 0, 4s 0, 3d5. So how will you fill the electrons? 1, 2, 3, 4, 5. Unless required, it is always electrons are always filled single filled. We do the single filled with electrons first, unless it is required for the pair. But in order to generate space for the electrons that will be donated by ligand, pairing of electrons will occur. That means these 5 electrons will pair in order to generate space. Since over here we are using hexa aqua, means 6 H2O molecules, each oxygen of water will donate 2 electrons. So 6 H2O molecules will donate 12 electrons. So we need to generate space for that. How we are going to generate space for that? We will be doing the pairing. These two electrons will go inside, okay, and will be generating space like that. So let me again just clear the screen. So for manganese H2O6, 2 plus manganese has a plus 2 oxidation state. Initially the electronic configuration will be like this: 1, 2, 3, 4, 5, S0, 4, P. Okay, 4S, 3D, sorry, 3D, 4S, 4P. But you know now, why will be pairing be occurring? There is 4D available. So there are two options: H2O, H2O. Okay, ligand donation. Ligand donation, let us consider in that way. Okay, if ligand is strong and ligand is weak. Okay, if ligand is strong, it will cause pairing. If ligand is weak, it won't cause pairing. That means in the case of strong ligand, this d electrons in the 3d will be paired and will be getting 3d5 like this: 3d5, 4s, 4p. Okay, 4s, 4p. In case of weak field ligands, the pairing won't occur and the 3d5 will have electrons like this and will be having 4s, 4p and 4d. So in the here ligands will donate their electrons. Let's suppose six ligands will be there. Let's suppose L, 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 L and L. The ligand this will donate over here. It's two electron cross cross. These two electrons will come from this ligand. Then this ligand will donate two electrons over here. This ligand will donate its two electron over here, and similarly this one over here. So 6, 1, 2, 3, 4, 5. Okay. Huh. 12 electrons will be donated, no? So it will be like this. D2sp3 will be the hybridization for the covalent bond generated via the donation of electrons from ligand to metal. Hybridization will be D2sp3 and such complexes are called inner sphere complexes. Okay. And in the case of weak field ligand, weak ligands won't cause pairing. So the ligands will be donating its electron to the outer d orbital instead. So six of the ligands will be filling four over here and two over here. So the filling will be like sp3d2. It is outer field coordination complex. It is inner and this one is outer. You got my point. So basically, Valence field theory gave some features or gave some postulates where they said that the ligands donate its electron to the vacant orbital of metal, and that's how they form coordinate covalent bonds. So if the ligand is weak, then it won't cause the pairing, and the outer field electrons will be formed, and outer orbitals will be filled, and if the ligands are strong, there will be filling of electrons, and inner orbitals of inner d orbitals will be filled, which will be caused to form electronic configuration. This, you got my point. So we'll do examples later. Let's just discuss all the postulates first. You understand how matter makes the space for the electrons that will be donated by the ligands. The second point is the vacant atomic orbitals of the metal are hybridized to form new set of equivalent bonding orbitals called hybrid orbitals. As I told you, these orbitals have same geometry and same energy and have definite directional properties. So by hybridization, what did you understand? By hybridization, they are trying to say that Mn2 plus over here, it will be forming hybridized orbital. After the shifting of electrons, there is the formation of this hybridized orbital as the ligands are donating electron in these orbitals. Okay, there is the hybridization of orbitals, and all the after the hybridization, there is no difference between them. This is the D2sp3 hybridization basically. And for this D2sp3 hybridization, what is the geometry? The geometry is octahedral. The Mn is inside and ligands are outside. So they form the same geometry. All the orbitals join in same energy. The hybridized orbital, we know what is a hybridized orbital. Different orbitals rejoin and rearrange their energy, and they then form hybrid orbital, which have same geometry, same energy, and it have different definite directional properties. Okay. The third point, the bonding Let me again just clear the screen. So the bonding in the metal complexes arises. The bonding in the metal complexes arises when the filled ligand orbital containing a lone pair of electrons overlaps with the vacant hybrid orbital and of the metal cation to form a coordinate covalent bond. I have already explained this, that metal has these vacant orbitals. Ligands have their own filled orbitals. So these orbitals and the vacant orbitals, they combine and form hybridized orbitals and form different hybridization complexes. Fourth point is each ligand has a set of one orbital containing a lone pair. Ligands will be only donating electrons if they have a lone pair or negative charge. Lone pair or negative charge. Pauling classified ligands in two categories: strong and weak. Strong ligands are those that will cause pairing of electrons present in the met, or metal or orbitals. Okay, and weak ligand won't cause any pairing of electrons already present in the metal. Okay, so example of weak field ligands are halogens, fluoride, chloride, bromide, iodide. Even H2 is an example of that weak field ligand. It is not strong. Strong field ligand examples are cyanide, carbonyl, etc. Okay, so coming to the other point for the weak valence bond theory. The strong ligands have a tendency to pair up the d electrons, as I have told and explained two times till now, that the d electrons of the metal and atom provide the necessary orbitals for hybridization. On the other hand, weak field ligands do not have a tendency to pair up the d electrons. The d electrons used in the hybridization may be either n minus d orbitals or inner n minus 1 d orbitals or outer n d orbitals. As I said, for the inner orbital complexes, the hybridization was 3d d2s 4s p3 4p3. Okay, the inner d orbitals were used d2sp3. So for the outer ones, actually 4d electron was being used, sp3d2. So this is the difference. Outer one is formed by the weak field ligands that are not strong enough to cause a pairing, while the inner one are formed by the strong field ligands. If unpaired electrons are present in the complex, then the complex is paramagnetic. For example, in nature, while if the electrons are paired, then the complex is diamagnetic in nature. This could be explained like this. Let us consider two examples: manganese hexa aqua 6 perchlorate, and other one you consider iron hexa aqua 6 perchlorate. Okay, in both the examples, what is the oxidation state of central metal atom? For in the case of manganese, H2O6, 2 plus is the charge over the coordination sphere, 2 plus. So how will you find the oxidation state? I have explained it many times. So again, x plus 6 into 0 is equal to plus 2, x is equal to plus 2. So manganese is in plus 2 oxidation state. Okay. So how will you, what is the electronic configuration of manganese? Manganese is an electronic configuration of 3d54s2. For the 3d54s2, if manganese 2 plus is present, these electrons from 2 from s orbital will be removed. So overall electronic configuration will be 3d5. 3d5, 1, 2, 3, 4, and 5. 5 boxes, 1, 2, 3, 4, 5. S is vacant and P is there. 4s, 4p. 3d5. Since H2 is a weak field ligand, it won't cause pairing. Rather, the ligand will be filled in outer d orbital. The 4d orbital will be filled. 4s, 4p, 4d. Okay. This 3d will remain singly filled only. 3d, 5. So the ligand electrons will be filled in this, like that. So sp3d2 will be the hybridization for this complex, and it will be outer field complex, outer orbital complex. Okay. Similarly, in the case of, and I was talking about the if unpaired electrons are present, since all the 5 electrons are unpaired, so the complex is paramagnetic. Okay. In the similar case, let us consider if there is no this CO6 molecule is present. Okay. Carbonyl is present. If it is a carbonyl is a strong field ligand. For strong field ligand like carbonyl, strong field ligand, let me just erase the screen. Okay, this much space will be enough, I guess, for now. So for strong field ligand, what is the electronic configuration of? How will we find the oxidation state? Oxidation state for FeH2O6 to Fe carbonyl 6 2 plus. Okay, X plus 6 into carbonyl is a neutral ligand again. So oxidation state for iron will be 2. Iron has an electronic configuration of 3d6 4s2. Iron 2 will be having electronic configuration 3d6. These two electrons will be removed. So how will be the filling of electrons if no ligands are present? 1, 2, 3, 4, 5, 6. Okay, first you do the all the singly filled fill all the orbitals singly, and then you do the pairing. So it is 3d6 4s0 4p0. When ligands are provided like carbonyl, which is a strong field ligand, it will cause pairing. How will the pairing occur? The d electrons present over here will be shifted to the other two half filled orbitals. So now the pairing will be like 1, 2, 3, 4, 5, 6, and two orbitals are vacant for the ligands to donate their electrons. So now when ligands will come, ligand. Okay, ligand will donate its two electrons each in this orbital, and so what we are having now, we are covering the inner orbital complexes. So we are forming an inner orbital complex with the hybridization of, what is the hybridization over here? D2sp3. D2sp3. Now talking about the magnetic property. Is there any unpaired electron present over here? All the electrons are filled. So the no unpaired electron. Therefore, no unpaired electron. Therefore, the species is diamagnetic. The complex is diamagnetic. I hope you guys understood. We'll further discuss the same and practice some more questions further in the video. So examples of octahedral complex. Let us just see how much you guys have understood. Inner orbital complex, we have an example of cobalt CN6 3 minus. First, you guys calculate the oxidation state of cobalt X plus 6. Cyanide has a charge of -1 into -3. X minus 6 is equal to -3. X will be having oxidation -6 plus -3 plus 6 is equal to +3. Cobalt has an oxidation state of +3. What is the electronic configuration of cobalt? Neutral cobalt 3d7 4s2. Cobalt has an electronic configuration of 3d74s2. If we have 3 positive charge on cobalt, that means the electronic configuration 3 electrons will be removed. 3d6 4s0. Okay. So now how will be the filling of electrons will be like? Filling of electrons will be 1 2 3 4 5 d orbitals, 1 2 3 4 5, and one paired s and 3d6 4s0 4p0. This is electronic configuration cobalt +3. We have here ligand cyanide. Cyanide is a strong field ligand. What will strong field ligand do? That will cause pairing of electrons. So when pairing of electrons occur, that means these electrons present in the outer d orbitals, these will be shifted in the inner d orbitals, and hence the overall electronic configuration will be like the 6 electrons will be paired in this fashion, 2 d orbitals will be vacant, s and p. Now if the ligand is donating its electron, how will the donation 6 ligands will donate its electron? 5 and 6. So this ligand will donate 2 electrons over here, over here, over here, like that. Okay. So what is the hybridization now? Hybridization is D2sp3. Are there any unpaired electrons? No. That means the species is diamagnetic. Okay. And this is an example of inner orbital complex. Since we are using inner orbital complexes are those where the d orbital used for hybridization is the n-1 d orbital. Okay. So if we are using n-1, that is the inner d orbital. That means that complexes are inner orbital complexes. I hope you guys understood. We'll do more examples. So for the inner orbital complex, as I said, the oxidation state of cobalt is we calculated it to +3. The valence shell cobalt +3 is 3d6 4s0. Cyanide is a ligand is a strong, therefore it will cause the pairing of d electrons. That means the space will be generated. All the 3d electrons is therefore paired, and the 3 of the 5d 3 of the 5 3d orbitals. That means there will be the vacant 3 orbital combined with the vacant 4s and 4p orbitals to form 6d2sp3 hybridization, as I explained. And therefore the complex is known has non paired electron. It is diamagnetic, and the hybridization is d2sp3. Hope you guys understood. The 6 hybrid orbitals overlap with the 6 filled orbitals of the ligand to form 6 coordinate covalent bonds. Okay. Now, please note this figure. So, cobalt has an electronic configuration of 3d7 4s2. This is how electrons are filled. Cobalt +3 has an electronic configuration of 3d6. So, how will be the filling of electrons? Like this. When hybridization occurs, these 2 electrons will be shifted in the inner d orbitals, and their space will be generated, and the ligands will come that will donate their electrons in the hybrid orbitals formed and form the D2 hybridization, D2sp3 hybridization octahedral geometry for the cobalt hexacyanide complex. Okay, this is an inner orbital complex. Example of one outer orbital complex is iron hexafluoro compound. So how what is the oxidation state? First, you calculate the oxidation state. Iron hexafluoro compound. Iron has an electron. So first oxidation state X is the, let's suppose X is the oxidation state for iron, plus 6 into 1 minus charge for fluoride, minus 3 X minus 6 minus 3 X is equal to plus 3 oxidation state. Iron has an electronic configuration of 3d6 4s2. Iron 3 plus will be having electronic configuration of iron 3d5. So how will be the electrons will be filled up in the iron 3 plus? 1, 2, 3, 4, 5. Since fluoride is a weak field ligand, it won't cause any pairing. No pairing will occur. Okay, no pairing will be occurring. Therefore, hybridization will be sp3d2. That means inner orbitals will not get paired and will not be involved in the metal complex formation. Rather, the electrons from the ligand will be filled in the outer d orbital. Okay, so outer 4d orbital nd. If n minus 1d electron is filled, that means an inner orbital complex is formed. If nd, that is 4d is filled, 4s, 4p, and 4d. So this is the filling when ligands donate their electrons. Then the complex is called outer orbital complex. Since fluoride is a weak field ligand, that won't cause filling. Therefore, the complex generated is an outer orbital complex. Is there any unpaired electron present over here? Yes, of course. 5 unpaired electrons are present in the inner d orbital. That means the complex is paramagnetic. Okay. In this complex, the oxidation state of iron is plus 3. We saw. So the electronic configuration of iron will be 3d5. We did solve the whole example. Fluoride is a weak field ligand, therefore no pairing of electrons will be occurring. All the 5 3d electrons are therefore occupied on 5 3d orbitals. The vacant 4s orbital combined with the vacant 4p orbital and two vacant 5d orbital out, outer orbitals, and they mix. It is actually 4d. So 4d orbitals and mix up with each other to form sp3d2 hybrid orbitals. These 6 hybrid orbitals will overlap with the 6 filled orbitals of the ligand to form 6 coordinate covalent bonds and form a outer sphere or coordination complex. This is the electronic configuration of iron 3d6 4s2. Iron 3 plus, it is 3d5. Fluoride is a weak field ligand. No pairing of electron. See, no pairing of electron. Rather, hybridization included outer d orbital, and the ligands then gave 6 ligands donated their 12 electrons in the outer d orbital and formed this coordinate covalent bonds. Okay, this is an example of outer orbital complex. Examples of tetrahedral complex we'll study now. For example, first example we'll study is nickel chloride, nickel tetrachloride ion. So nickel has calculate the oxidation state first. Nickel chloride, nickel tetrachloride, 2 minus. X minus X plus 4, oxidation charge on chloride is minus 1, equal to minus 2. X minus 4 is equal to minus 2. X is equal to minus 2 plus 4. X is equal to plus 2. Okay. So nickel, what is electronic configuration? It is 3d8 4s2. What will be the electronic configuration if it is at a charge of plus 2? It will be 3d8. Okay. So, but how will be the electrons filled? if no ligand are present. 1, 2, 3, 4, 5, 6, 7, 8. 4s vacant, 4p vacant. 3d8, 4s0, 4p 0. Now, if ligands are coming, that is, if chloride is a weak field ligand. Chloride is a weak field ligand, it won't cause pairing. That means these two electrons present over here will remain in this fashion only, and 4 chloride ions will donate electrons in outer orbital only. So the 4s orbital over here and 4p over here, they do hybridization and will form hybrid orbital where 4 ligands, that is 4 chloride ions, will donate their 2 electrons each in the empty orbitals, and the hybridization generated will be sp3. So what will be the geometry? Geometry will be tetrahedral. Are there any unpaired electrons present in this complex? Please pay attention that there are 2 unpaired electrons present. So what will be the magnetic behavior? It will be paramagnetic. And the complex generated is an outer orbital tetrahedral complex. Okay. If the outer orbitals are involved in the formation of a tetra-coordinated complex, then the shape will be tetrahedral. If the inner d orbital is involved, then the shape will be square planar. We discussed example of that as well in the further slide. So in this complex, the oxidation state of nickel is +2. We calculated that. The valence shell electronic configuration of nickel +2 will be 3d8 4s0. So, cis chloride is a weak field ligand. As I said, there will be no pairing of electrons will occur in the 3d orbital. None of the 3d orbital is vacant. Vacant 4s and 4p orbital combined to give a 4sp3 hybridized orbital. Okay. Sorry, my charger was disconnected. So where was I? I was saying that the hybridization will be sp3, and the 4 hybrid orbitals formed, that is sp3 hybrid orbitals formed, will join with 4 ligands and will form coordinate covalent bond, and the geometry for that sp3 hybridization will be tetrahedral. Since unpaired electrons will be present in the inner 3d orbital, so the complex will be paramagnetic. Okay, so please see the proper diagram for that complex. Nickel 2 plus. Nickel atom has electronic configuration of 3d8, 4s2, 4p0. Nickel 2 plus. 2 electrons will be removed from this electronic configuration, 3d8, 4s0, 4p2. Now 4 chloride ions are supposed to come, so the hybridization will occur including the outer d orbital, outer orbitals only. No pairing will be occur in the inner one because chloride is a weak field ligand. That means hybridization will occur, and the hybridization will be sp3, and 4 ligands will come donate their electron in these hybrid orbitals, and the complex generated is an outer orbital tetrahedral complex. Example of an inner orbital tetrahedral complex is nickel cyanide tetracyano complex. So in this case, what is the oxidation state of nickel? You do calculate by yourself only, otherwise you won't be able to perform well in the exam. So nickel plus 4 minus 1, charge on cyanide is -1. So nickel plus oxidation charge on X, let's suppose what is X is a charge on nickel. So +4 minus 1 into -1 is equal to overall charge is -2. x minus 4 minus 2, x is equal to plus 2. So nickel has an electronic configuration of 3d8 4s2. Nickel 2 plus has an electronic configuration of 3d8. How will you fill it? You will fill it like this: 1 2 3 4 5 6 7 8. 4s vacant, 4p vacant. Okay, 3d8. Cyanide is a strong field ligand now. What will cyanide do? Cause pairing. So the d electrons present inside will be paired. This electron will be paired over here. And now what will be the electronic configuration? Electronic configuration is 3d8 only, but now the filling of electrons will occur and one vacant orbital is present in the inner d. So we have this electronic configuration now, that is 4s and 4p. Now how will be the hybridization will occur? Hybridization will include this inner d and it will be like dsp2. This is the hybridization dsp2. 4 ligand cyanide will come and they will donate their electrons in these hybrid orbitals XX, XX, XX. So the geometry for the complex dsp2 generated is square planar. This is the difference basically. If the inner d orbitals are used, then that means the geometry will be a square planar and the hybridization is dsp2. If the outer d orbitals are used for the tetrahedral complex and the tetracoordinated complex, then the geometry will be tetrahedral and the complex hybridization will be sp3. Here please see, do we have any free electrons? Since there are no free electrons, no unpaired electrons, sorry, unpaired electrons, that means the species, what is the species? It is a diamagnetic species. Okay, I hope you guys are understanding. I'll give you some examples as a homework. Please do them. So in nickel, in this complex, nickel oxidation state is +2, and the electronic configuration of nickel in +2 oxidation state is 3d8 4s0. Okay, so cyanide is a strong field ligand. It will cause the pairing to pair up the two unpaired electrons and one d orbital, resulting in the vacant, in a vacant 3d orbital. We have already seen that. This vacant 3d orbital get hybridized with a vacant 4s orbital and 2 4p orbital to generate a dsp2 hybridization. And the d2 is the 4 hybrid orbitals form bonds with 4 ligands by sharing of 4 pairs of electrons, and thus the complex form is a square planar complex. Square planar. And since no unpaired electron is present, that means it is a diamagnetic complex. Okay. Magnetic properties of coordination compound. Magnetic properties are basically a coordination compound is paramagnetic in nature. In all the examples discussed above, I have already explained that if unpaired electrons are present in a coordination compound, that means the coordination compound is paramagnetic. And if all the electrons are paired, that means the complex is diamagnetic. So, depending upon the number of unpaired electrons present, you can calculate the magnetic moment of a coordination complex. Okay, magnetic moment of a coordination complex. It is a basically an experimental property. It is an experimental property. So, from experiments or by using different instruments, you first calculate the magnetic moment. Okay, if compound has some magnetic moment, then only you can say that there must be some unpaired electron, unpaired electrons. And theoretically, how can you calculate the magnetic moment? You can calculate the magnetic moment by this using this formula: mu is equal to under root n into n plus 2, where n is the number of unpaired electrons. Okay, n is the number of unpaired electrons. For example, if was some compound has one unpaired electron, the magnetic moment will come out to be 1.72, around 2.83, around 3.9, 4.9, 5.9. It is just simply some rough calculations that if some unpaired electrons are present, the value of magnetic moment will be like this. So calculate the magnetic moment for these complexes. Let us calculate the magnetic moment for these complexes. Cobalt hexacyano complex. What is the oxidation state? Now I hope you guys can calculate cobalt hexacyano complex. Let us take cobalt as an oxidation state or charge of X. X plus 6, cyanide has minus 1, minus 3. It comes out to be X minus 6 minus 3. X minus 3 plus 6, X comes out to be plus 3. Cobalt has plus 3 charge. Okay, plus 3 oxidation state. Electronic configuration of cobalt is 3d7 4s2. Cobalt plus 3 will be 3d6 4s0. Do the filling of electrons by yourself. Please do these examples by yourself. This is how you will fill the electronic configuration. 6 electrons in the d orbital. Okay. Now, how will the hybridization will occur? Hybridization will occur. First, see the ligand cyanide. Cyanide is a strong field ligand. What will it do? Cause pairing. These two electrons will be paired up, and thus new vacant orbitals will be generated in the inner d orbital. 1, 2, 3, 4, 5, 6. This is the new electronic configuration now. Now hybridization will occur. These 6 orbitals will hybridize to give an hybridizations D2sp3. These 6 hybridized orbital will combine with 6 ligands of 6 cyanide ligands and do the uh, metal complex formation. Okay. So are there any unpaired electron present? The question was is what is the magnetic moment in this complex? Since there are no unpaired electrons present, how will you calculate? Mu is equal to under root n into n plus 2. This is the formula. Okay. N is the number of unpaired electrons. N is equal to 0. So what will be the value? 0 into 0 plus 2. Under root 0. Magnetic moment will be 0 only. Okay. It is a diamagnetic complex. It won't be having any magnetic moment. I hope you guys understood. I'll give you 5 minutes to solve other example. Please do solve this iron hexafluoro complex example. Shall I solve now? I hope you guys have solved. So in this complex oxidation state of iron, X plus 6 minus 1, fluoride has a charge minus 1, minus 3, X minus 6 minus 3, X is equal to minus 3 plus 6, X is equal to plus 3. Iron has an electronic configuration 3d6 4s2. Iron 3 plus will be having an electronic configuration 3d. Remove 3 electrons from here, 3d5. Okay. Fill this electronic configuration in the orbitals. 1, 2, 3, 4, 5, 3d5, 4s vacant, OP vacant. 4s4. So fluoride is a weak field ligand. Will it cause any pairing? Tell me. No, no pairing will be there. No pairing of electrons. Therefore, in hybridization, outer d orbitals will be involved. Will be involved. Therefore, 3d will remain as it is, having 5 electrons. 4s, 4p. This will be 4d. 4s, 4p, 4d. Hybridization will include outer 2d orbitals. So this will be the hybridization. sp3d2 ligands will donate their electrons in these hybrid orbitals and form the metal coordinate complex. Okay, so the point is this compound paramagnetic? Yes, there are basically 5 unpaired electrons. You can say 5 unpaired, C 5 unpaired electrons. So what will be the magnetic moment? N into n plus 2. Calculate the value. N is the number of unpaired electrons. Number of unpaired electrons over here are 5. So 5 into 5 plus 2. Solve this thing. The value will come out. Please do the calculation and solve it. We'll come to the next example. Clear screen. The next example is nickel tetrachloro complex and the other one is nickel tetracyano complex. So solve these two examples. I'll not explain in detail as I explained before. So I'll be doing them very fast. The oxidation state of nickel will be 2 plus. 3d8 will be the electronic configuration. Since it is a weak field ligand, so the filling will be like no pairing of electrons will be occurring. So the filling will be like this. Since it is contains 4 ligands, so it will be needing 4 hybrid orbitals. 4 hybrid, since there are no no empty orbitals present in the 3D, so hybridization will include outer orbitals only. Sp 4s and 4p. Hybridization will be equal to sp3. Ligands will donate electrons in these hybrid orbitals, and therefore the hybridization is sp3. The shape will be tetrahedral. Talking about the magnetic moment, under root n into n plus 2. 2 unpaired electrons are present. So how will I solve? 2 into 2 plus 2. 2 into 4. So it is under root 8. Magnetic moment is under root 8. Similarly, in the other example, nickel has an electronic configuration of nickel has a charge plus 2. 3d8 is the electronic configuration. Filling will be like this, but here the filling will be like this. Since it is a strong field ligand, it will cause the pairing. One 3d vacant orbital is present, so hybridization will be like this: dsp2. dsp2 ligands will donate electrons in these hybrid orbitals, and therefore hybridization will be dsp2. Complex will be square planar. Since unpaired electron, number of unpaired electron equal to 0, magnetic moment will be n into n plus 2. Under root n into n plus 2, magnetic moment will come out to be 0. I hope you guys understood. So now we'll talk about the limitations of valence bond theory. Valence bond theory told us that the ligand metal has hybridized orbitals, has empty hybridized orbitals, Ligands donate electrons from their filled orbitals to these vacant hybridized orbitals, and metal ligand coordinate covalent bond is generated. Okay, So you understood all these factors, but there are certain limitations with this valence bond theory. That includes, it could not explain the nature of ligand. They just simply said that some ligands are strong that will cause pairing, like this carbonyl, NO, etc. These are strong, and some are weak, like chloride, fluoride, halogens, basically water. These are weak. But they couldn't explain why some are weak, why some are strong. What is the reason? They just simply said some are weak and some are strong. That will cause a pairing depending upon the experimental magnetic moment value that they calculated. So they could not explain why the pairing of electrons occur in the presence of strong field ligands. They couldn't explain so. They could not explain the color and electronic spectra of the complexes. Some complexes having unpaired electrons, they were showing colors, and some having paired electrons, they were not showing any colors. So they could not explain anything about the electronic spectra, the color of the complexes. They could not explain the reaction rates and the mechanism of the reaction complexes. They could not explain these complexes in detail. They were just saying that some complexes are strong, some complexes are weak. What is the reason behind that? This theory could not explain that. The theory does not provide any quantitative interpretation data because of the thermodynamic and kinetic stability of the about the thermodynamic and kinetic stability of the coordination complex. This was another limitation. So the theory contains a number of limitations, and thus it needs to be modified, which was further done by the crystal field theory. The next theory that we'll be studying is the crystal field theory, that suggests that metal and ligand has a ionic bond between them. Ionic bond. Here the bond suggested was coordinate covalent bond. In the VBT, its valence bond theory, the coordinate covalent bond was there, coordinate covalent bond. But in the next theory that we'll be discussing, they are saying that the metal and ligand has an ionic bond between them. So we'll discuss in that theory, and we'll talk about these limitations, how the limitations were um, explained in the next theory. These are some examples that I want you guys to do and practice and find out the hybridization of these complexes, their shape, and find out whether the complex is diamagnetic or paramagnetic. We will discuss some examples in the next video, and some other questions as well for the VBT. And thanks for watching. No, we'll discuss summary first. So here we discussed valence bond theory. Valence bond theory says that metal and ligand contains a metal coordinate covalent bond. Metal has empty hybridized orbital. Ligand is filled hybridized filled orbitals. Those filled orbital combined with the empty hybridized orbital and forms coordinate covalent bonds. Okay. Features, we understood that metals does the hybridization and does the pairing of electrons depending upon the nature of the ligands. So we did solve some examples that if the inner d orbitals are involved, then in the case of strong field ligands, if the inner d orbitals are involved in hybridization, like D2sp3 is the hybridization, that is an inner orbital complex. If the ligand is weak enough, it is not causing the pairing of electrons and no inner d orbital is available for hybridization, then the hybridization is generally sp3d2. In that case, outer d orbital is involved. That's why it is called outer orbital complexes. Similarly, for the case of tetrahedral complex, if the ligand is weak, it won't cause any pairing of electrons. So inner d orbital is not available. So the hybridization is sp3. Then the shape also varies. That forms the shape tetrahedral. While in the case of strong ligands, four strong ligands, that will cause a pairing of the electrons in the presence in the d, that will make the d available, inner d available, and the hybridization will be dsp2. In that case, the geometry will be square planar. We discussed this, and we discussed about the magnetic moment. Magnetic moment could be calculated by depending upon the number of unpaired electrons. If number of unpaired electrons are present, that means the compound is paramagnetic. If not, that is diamagnetic, and this is how you calculate the magnetic moment, where the n is equal to the number of unpaired electrons. We also discussed the limitations of the VBT, that it cannot explain the color spectra, electronic transitions, why ligands are strong, why ligands are weak. We'll discuss all this in the next video. Before that, we'll do some practice for finding hybridization of the complexes in the next video. Thanks for watching.